just a little bit of a recap on redox then. Can you tell me what conditions are required for a redox reaction to occur?
You have to have a strong reducer and a strong oxidizer.
Yep, so the strong oxidizer reacts with the strong reducer. For spontaneous redox. And we have looked at, thinking about this in the context of maybe we have a test tube or a beaker, and we might have a piece of, let's just say that this is magnesium, and the solution is silver nitrate. What would you think might happen?
Metal displacement.
Metal displacement? And what does that look like then? Or how do we express our thinking in terms of redox? Yep. So what would one of the half equations be? And someone else want to tell me what kind of half equation this is?
Oxidation.
Yeah, oxidation. And what's the other half equation then?
Silver plus 2 electrons. The silver. Silver.
How about we look on our ECU? What is it? Is it just one plus?
Yeah.
Okay.
And plus an electron.
People putting a 2+ charge on their silver ion is actually a pretty common mistake. So if you're not quite sure, just check up on your electrochemical series. Yes, and so what would we need to do to balance this then?
Multiply to have the same electron.
Okay, so this is a reaction that's happening in that little test tube there. What is unique about a redox reaction? Like, what is involved in a redox reaction?
Elements.
Elements? Doesn't always have to be elements.
Transfer of electrons.
Transfer of electrons. Okay, so for redox, what we have is a transfer of electrons. In what other context can you think of something in your everyday lives where there's a transfer of electrons?
Batteries.
Like
Electricity.
Static?
Electricity.
Electricity. Yeah, so, well, in static electricity, we get a charge build up, and when it discharges, it's very rapid. But we have a transfer of electrons in electricity. Yeah, that's right. And because of that, we can separate these out. So just say, instead of having them just in the one test tube there where we can't harness this transfer of electrons, it's because it's happening all in the one container, I could instead have 2 beakers, and in this beaker I will have silver nitrate solution, and in this beaker I'm going to have magnesium nitrate solution. Right, and I have to put the line across there to indicate that there's something in there. If I don't have the line, the beaker's empty. And for each of these beakers, there'll be the corresponding metal. So we've got the silver ion here, so I need a silver electrode. Right, this is an electrode. And this one is a magnesium electrode. And what we're trying to do here is set up a cell. What would I need to do next, do you think? Because if I can get these electrons moving, I can generate some electricity. What do I need to do? Circuit? Yeah. So I need some wires. And I'll probably just put in a voltmeter. An ammeter or a voltmeter is going to allow me to make some measurements here. Mostly we're using the voltmeter so that we can measure the volts generated. Now, this wouldn't really work for any length of time. Why not? What are we missing? Got an idea? What do we need for a circuit to work? Sorry?
To be completed.
Yeah. So at the moment, the two beakers are separated and they're not joined together, and so we need to join the beakers together with what we would use as a salt bridge. And so now we have a complete circuit, and we can figure out which one is going to be oxidized and which one is going to be reduced, and we can also see what kind of voltage would this cell generate. Okay, just like in your mobile phones, it's not silver and magnesium, but you've got a chemical reaction in your batteries occurring all the time that is providing the voltage to operate your device. Now, we've already decided that what would actually happen is a reduction reaction at here with the silver, isn't it? So this same reaction that would happen in the test tube or here can happen in the beakers separated out. All right, so we would still be looking at oxidation and reduction reactions that we've got there. And in fact, I might move them around because, sorry about this. Just because this is what I want you to do, is to always put the oxidation reaction on the left-hand side. Sometimes you'll come across questions where it's trying to trick you by putting it on the other side, but whenever you're drawing out an electrochemical cell, which is what this is, to draw it out this way so that the oxidation reaction is on the left-hand side. that's the half equation for that reaction. I've included the spectator ion when I've here just saying what the solution is. But that doesn't really figure much in as far as the reaction is concerned. The way I'm going to represent this oxidation on my drawing of my electrochemical cell is to indicate an arrow away from the electrode and then writing the Mg2+ there, just to show that the magnesium ion is coming off the electrode. So oxidation is occurring there. And we already know that this is our half equation for the silver. And again, the way I can represent this on my electrochemical cell diagram is by writing the ion. It's not really very well there. But this time the arrow is onto the electrode. Now, we have special names for our electrodes. And the electrode where oxidation occurs is called the anode. And the electrode where the reduction is occurring in our electrochemical cell is the cathode. Now, if we look a little bit closer at this diagram here, if I have producing these magnesium ions here at this anode, what's going to happen with the electrons? Where are they going to be generated and where are they going to travel to? Which direction do you think the electrons go? From the anode to the cathode. Okay, so our electrons are going to be traveling in this direction. Because if I've made this 2+ ion, then I've also generated 2 electrons at the same time, haven't I? And then they're going to travel up through the wires and come down to the cathode, where they're going to be available then for the silver ion to pick up to then reduce to become solid silver on the electrode. Does that make sense? Yeah? Okay, so then what do you think the charge on the anode is? And what's the charge on the cathode? Remembering that like charges repel and opposite charges attract. What's the charge on the cathode? Positive, because we're attracting these electrons. What's the charge on the anode?
Negative.
Negative, because we're repelling our electrons. Now, the last thing that we need to talk about here is the salt bridge. When we're making a salt bridge, we soak some filter paper or some other strip in a concentrated, saturated salt solution so that there are plenty of ions present to keep the cell operating. What kind of salt solution do you think would be appropriate to use as a salt bridge?
Something nitrate.
A nitrate. Why do you think a nitrate? That's a good thought.
Because then it won't react.
So for a salt bridge, we want a nitrate ion because it won't precipitate And what else can't we do?
Can't be reduced.
Is it reduced or oxidized?
One of them.
Probably oxidized. Okay, so we've got our nitrate ion. What's going to go with our nitrate? There's got to be something with it. There's got to be something nitrate.
Sodium.
Sodium nitrate. Okay, sodium nitrate. Why would we choose sodium?
Because it can't be reduced in a solution.
Can't be reduced. And
It won't precipitate.
it won't precipitate. So the way we would normally write that would be like sodium nitrate like that. Potassium nitrate would also be appropriate for the same reason. Yep. Very good. Now, let's have a look at the movement of our ions in the salt bridge. Which direction do you think the nitrate is going to move? So if I write up here, I'm just going to write the sodium ion and the nitrate ion. Which way is each one going? So which direction is the nitrate ion heading? Towards the oxidation half cell or the reduction half cell? Okay, we've had a couple of suggestions.
The oxidized from
Light charges
If you're going, yeah, if you're going the other way to that one, so if you're going from the silver from the cathode to the anode.
The nitrate, just say it's just in the salt bridge here. Is it travelling towards the anode or the cathode? The cathode?
It's negative.
What do other people think? Anode or cathode? Oxidation or?
It's going the wrong way.
Should be the nitrate would be travelling to the anode.
Because
You have Mg2 plus ions.
it's actually travelling in this direction because we needed to balance the charges of the ions that we're producing. And so the nitrate heads towards the oxidation half cell. And the same thing here, our sodium ions are going to travel in this direction because they're going to replace the silver ions that are removed. Every time a silver ion is removed, we need another positive charge to come down to balance that charge. So we've got a movement of
I
ions.
just noticed it wasn't big. Where do you remove to? Aren't I just removing the electrons?
The silver ions are being removed from solution because they're being reduced. So every time this happens,
What makes them
I'm
made
forming a
of solid?
precipitate.
it's not a precipitate. Okay, this is a reduction reaction where we're producing a solid, but it's not a precipitate. Because a precipitation reaction is the attraction of ions to then form an ionic solid. Whereas this is a reduction reaction. Where it's taking an electron and becoming,
So it's becoming a solid, but
it's becoming a solid, and what we end up with is a deposition then of the silver out of the solution onto the electrode. So the cathode is going to get bigger as it has this build-up of the silver ions on it, which become silver metal. So every time a silver ion is reduced onto the surface of the cathode, we need to replace that with another positively charged ion to keep the charge balance correct. And this electrode, the anode, is going to get eaten away as we lose the magnesium from the anode into the solution, the Mg2 plus ions. So our anode it gets smaller and our cathode builds up. Okay? Does that sort of make sense? Yeah, almost. And the way you remember this, oxidation at the anode. Okay, so make sure that your oxidation half cell is the one you draw on the left, and that's where oxidation is going to occur. The rest of it then should follow on from that. Our electrons are going to be moving away, and our anode has a negative charge. Okay, and we have